Hi, this is Professor Earth, and we're going to find out what happens next at the Doomsday Glacier in Antarctica. What happens next as global warming continues and the Doomsday Glacier, creates doom. So to do this, let's go to Antarctica. There's no point talking about it here in a classroom or on your phone. Let's actually go to Antarctica and look at things. The absolute best way to go to Antarctica would be to take a sailboat. So we'll get in a sailboat, we'll cruise down, we'll anchor off, and we'll take our little Zodiac into shore. And when we get there, we'll see penguins. Thousands of penguins, tens of thousands of penguins, playing on the shore, playing on the ice. And we'll see leopard seals. Now, you might think there's no predators for penguins in Antarctica, but the leopard seal is a deadly predator. And you wouldn't think it when you see the two together on land. Here's a leopard seal coming on shore to harass a little colony of penguins. And the penguins aren't scared at all because they know the leopard seal can't move very fast on land. They seem to almost tease the leopard seal. They walk slowly away. Some of them then walk towards the leopard seal because they know it can't move fast enough. It's not in its element on land, but at sea, the leopard seal can take the penguins. It can be faster than them, can go into a flock of them in the sea and rip them with its teeth and take them and eat them. One of the saddest things about the Doomsday Glacier is what it's going to do to the local populations in Antarctica, the penguins, the leopard seals, the whales. It's going to utterly change the environment there, but I'm getting a little ahead of myself. So let's look a little higher. We'll climb up onto the glacier. There's still some penguins. And up above us, we'll see the ice sheet. So this is what we want to look at. What's going on with the Antarctic ice sheet and the Doomsday Glacier? The Doomsday Glacier, or the Thwaites Glacier, has been in the media recently because of an important scientific study by Schukel and his colleagues looking at widespread seawater intrusions beneath the grounded ice of the Thwaites Glacier. And they did this using satellite imagery. They took a series of images and then they overlaid them, and there would be interference between the two where there was some difference in elevation of this glacier. And in this case, it's because of the tides and the seawater coming underneath the glacier, lifting it up, putting it back down with tidal cycles. So there's interference, which shows up as this series of rings called interference figures in the imagery. And the reason this study gathered so much attention is the interference figures can be traced as much as 5 or 6 miles up underneath the glacier. So that means that warm seawater is penetrating that far underneath the Doomsday Glacier. But that's not why there's doom. So let's get into this doom thing. The first thing we have to do is look at the Antarctic ice sheet as a whole. And we see that it's divided into 2 parts. There's a high elevation part on the right here, and a lower elevation, tinted in red, on the left. These 2 parts of the Antarctic ice sheet are so different that we can actually subdivide the ice sheet into 2 different ice sheets. The East Antarctic ice sheet, the high one on the right, and the West Antarctic ice sheet, the low one on the left. The dark blue dots on this map show the location of subglacial lakes, and they're mostly concentrated under the East Antarctic ice sheet. So you might think this is the less stable one, but you'd be really wrong, because although there aren't lakes under the West Antarctic ice sheet, it turns out its base is actually below sea level. Now let's zero in on the West Antarctic ice sheet. If we look at this map, we can see that the West Antarctic ice sheet is divided into about 5 different drainage basins. And the Doomsday Glacier, the Thwaites Glacier, along with a similar glacier, the Pine Island Glacier, are on the far western edge, and they're draining into the ocean on that side of the Antarctic ice sheet. This next image shows the amount of global warming going on in Antarctica. And the West Antarctic ice sheet is warming much more rapidly than the East Antarctic ice sheet. So the Doomsday Glacier is affected by this warming, but it's not the real problem there. Most of the ice loss at the Doomsday Glacier doesn't happen because the air is warming and the glacier is melting. Ice is lost from this glacier because as the ice sheet enters the sea, it converts into an ice shelf, and it calves off into huge icebergs, and these drift away, and that accounts for the mass loss at the Doomsday Glacier. And this mass loss by calving is accelerating because warm currents from the warming ocean are now penetrating underneath the ice shelf and underneath the main glacier itself. They're thawing this from the bottom, and that's causing more rapid retreat than we've seen in the past. And while the Thwaites Glacier, the Doomsday Glacier, gets most of the media attention, the same thing's happening at other glaciers. The Pine Island Glacier next door has the exact same process, causing melting and retreat and accelerated calving of this glacier. And now we're getting to the heart of the doom issue, because as these glaciers retreat, and they don't have to retreat very far, they're going to get closer to the center of the ice sheet, which is underwater. It's marine-based, so the water will get deeper and deeper where the ice shelf is calving off if these glaciers start retreating back towards the center of the West Antarctic Ice Sheet. Now let's look at a cross-section of the West Antarctic Ice Sheet. So you can see on the map A to B, that's where we're taking our slice, and it's shown above. And as we do this, we see that in the center of the ice sheet, it's as much as 2,000 meters, or well over a mile below sea level, in the center of this ice sheet. It's filled with ice now, but as the ice sheet retreats, as the calving occurs, very, very deep water is going to be present where the calving is going on. This calving retreat right into the center of an ice sheet, into very deep water, is something that isn't happening anywhere on Earth today. So we don't exactly know what will happen, but we know this happened in the ice ages when we destroyed the huge ice sheets that were here and covering places like Hudson's Bay. And we know that their retreat was very, very rapid. So let's look at some equations to try to understand what would happen as the ice sheet retreats back into very deep water. The first equation we looked at was published by Terry Hughes, and this is an equation that tries to describe the physics of ice calving where an ice glacier encounters water. So it has factors in it like the density of the ice and the amount of water within the glacier and how much tidal forces are exerting. But Terry Hughes says, well, we can't use this at deep water. It's only appropriate where a glacier is sitting on land and being acted on by tidal forces. So that one doesn't even work. So basically, if we're trying to look at this physically, we have to combine a glacier flow model with some kind of mechanical ice calving model. It's very, very complicated, but there is a simpler way to do this. Let's look at an empirical model. And Pelto and Warren have created such an empirical model. It's very simple. It just says you see the velocity of glaciers calving is equal to some number plus 0.008 times the depth of the water that it's calving in. So it's directly proportional to the calving water depth. So Pelto and Warren created their model by cross-plotting actual calving velocities at glaciers from Greenland, Alaska, other sites around the world of all types, cross-plotting against water depth. And the implication of their model is very, very significant. If we look at Antarctica, the Doomsday Glacier, let's say modern glaciers are calving into about 20 meters of water. And as it retreats, it moves back to 200 meters of water. The calving rate is going to go up by 10 times. Let's say it goes into 2,000 meters of water, the calving rate will go up by 100 times. The calving rate is the rate at which ice is being removed, the velocity of ice moving out from the glacier front. 100 times more rapidly in deep water will mean huge amounts of ice moving out of the ocean where it'll melt and it'll raise sea level. Enough ice melt to literally eat out the center of the West Antarctic Ice Sheet and destroy it, and enough melt to raise sea levels around the world by 5 meters, 10 meters, 15 meters, and this will have a catastrophic effect on cities and coastal areas around the world. Hence the name, the Doomsday Glacier. And just to make everything even more doom-friendly, once the glacier starts to retreat, it's unstoppable. It's simply controlled by the depth of water. Doing something about climate change, reducing CO2 emissions, there's nothing we can do once this glacier starts to retreat by rapid calving. We're set on this course. It's inexorable, it's unstoppable, and it's going to bring doom. Okay, well, I hope everybody's having a great day out there. We're having lovely weather up here in central Alaska. A little bit warmer than it should be, but where isn't it warmer than it should be? Okay, have a good one.